Welcome to The Explainer. Today we are diving into one of the absolute coolest geological mysteries hiding right under our noses. Well, technically, deep beneath the ocean's surface. We're talking about the Chagos-Laccadive Ridge. This is a massive underwater mountain range, stretching roughly 2,500 kilometers off the western coast of India. Now, up on the surface, it just looks like your standard tropical paradise, right? But as we decode the tectonic data today, we're going to see that its deep geological roots actually tell this wild story of ripping continents, massive volcanic eruptions, and honestly, a massive case of mistaken tectonic identity.
But before we get ahead of ourselves, to really understand what we're looking at here, we need to talk about the concept of a microcontinent. And it's pretty much exactly what it sounds like. It's a literal fragment of continental crust that is completely broken off from a main continental mass. Over millions and millions of years, these rogue fragments usually sink, they get completely submerged, and they get heavily altered by volcanic activity. Now, what's so fascinating for us today is that the Laccadive Ridge, which is super famous for its beautifully simple, shallow coral atolls, might actually be hiding one of these massive ancient continental fragments deep down in its foundations.
Which naturally brings us to the central mystery of our explainer today. How in the world does a massive piece of a continent, a literal chunk of the Earth's continental crust, just hide in the middle of the Indian Ocean? Seriously, how does something as unimaginably huge as a continental sliver go completely undetected beneath a delicate layer of coral reefs? To solve this, we're going to have to look way past the surface and play geological detective. So let's ground ourselves geographically for a second. Picture the western continental margin of India. Running almost perfectly parallel to that coast is this incredibly extensive ridge system. The whole thing stretches way down south to the Chagos archipelago, but we are focusing specifically on that northernmost segment right next to India. That is the Laccadive Ridge. It sits there acting as this massive underwater plateau, a bathymetric high, and it's totally surrounded by really deep oceanic basins.
Part 1. Oceanic track or continental sliver.
For literally decades, scientists have fiercely debated the true tectonic origin of this massive underwater structure. It's basically been a heavyweight match between two main models. In one corner, we have the hotspot trail model. This was the traditional, widely accepted view. It argued that as the Indian tectonic plate moved rapidly northward millions of years ago, it dragged over the Reunion mantle plume. Think of that plume as a massive blowtorch of magma blasting up from deep inside the Earth. The idea was that this blowtorch melted the oceanic crust, leaving behind a trail of oceanic volcanoes that eventually built the ridge. But in the other corner, we had the continental sliver model. This model suggests something entirely different, that the ridge is actually a broken, heavily stretched piece of the ancient Indian continent itself, completely ripped away during the breakup of the supercontinent Gondwana. So which one is it? Well, let's look at the clues. Part 2, X-raying the ocean floor. To figure out what the ridge is actually made of, scientists essentially X-rayed the ocean floor using deep seismic refraction. They bounce sound waves deep down into the Earth's crust to measure exactly how fast those waves travel, because that speed tells us exactly what kinds of rocks are hiding down there. And the data they got back? It revealed two massive anomalies. First up, the depth. The crust down there goes deep, roughly 25 to 27 kilometers. Just to put that into perspective, normal oceanic crust is really thin, usually only about 6 to 7 kilometers thick. So right away, that is a massive red flag that we aren't just looking at regular ocean floor. Second, when they looked at the acoustic speeds for the upper crystalline crust, the waves were traveling between 5.4 and 6.3 kilometers per second. Why does that matter? Because that specific speed is the literal acoustic fingerprint of granitic continental rock. It is absolutely not the basalt you would expect from a standard oceanic volcano. But wait, there's a catch. When scientists measure the structural strength of the ridge, which they call the effective elastic thickness, they got a shockingly low number, just 3 kilometers. Think of the Earth's outer shell like a rubber band. A normal, ancient continental plate, it's thick, it's rigid, it's strong. But the lithosphere under the Laccadive Ridge, it's like a weakened, old, stretched-out rubber band that has completely lost its snap. It's incredibly flimsy. So the big question becomes, if this is a continent, why on Earth is it so weak?
And the answer lies in how this crust was deformed. The crucial thing to understand is that the Laccadive Ridge is a total geological Frankenstein. because that continental rock had already been stretched and weakened so severely during the rifting of India. When that reunion hotspot blowtorch finally hit it, the rock was too flimsy to support the weight of erupting volcanoes. So instead of building massive mountains on top of the crust, unbelievable amounts of heavy, dense magma actually injected and pooled at the very bottom of the crust. Geologists call this process magmatic underplating. The magma essentially formed this 8-kilometer thick supportive cushion deep underground, and that cushion is literally what keeps the whole structure from just sinking straight into the mantle.
Part 3. Dating the deep sea rocks.
Okay, so to finally settle this debate once and for all, researchers knew they needed physical samples. They needed the smoking gun. So they drilled nearly 2,300 meters deep into a structure called the Padua Bank on the northern ridge. They bypassed all the coral, they bypassed all the sediments, and they managed to pull up samples of rhyolite. Rhyolite is a highly acidic rock that is classic textbook continental crust. Using super high precision argon-argon isotope dating, they pinpointed the exact age of these deep sea rocks. And the results were stunning. 76.2 and 77.5 million years old. When you map this out, these ages line up perfectly with similar continental rocks found right on the Indian mainland.
And this data, it completely obliterates the traditional theory. You see, the rocks making up the ridge essentially have fake IDs. For years and years, because the entire ridge is carpeted in this thick layer of flood basalts from the reunion hotspot, scientists just assumed the whole thing was created by the hotspot. But here's the catch. The reunion hotspot didn't even hit this area until about 60 to 65 million years ago. Our deep sea rhyolites are 76 to 78 million years old. They strictly predate the hotspot. This proves definitively that a piece of continental crust was already sitting right there, undergoing volcanic rifting long before that giant mantle plume ever showed up.
Part 4. A Tale of Two Tectonics.
So the big takeaway here is that it's not an either-or situation. It's actually both models working together. Let's synthesize all these tectonic clues into one cohesive timeline. Here's exactly how it all went down. Around 88 million years ago, India aggressively separates from Madagascar. This causes violent, prolonged stretching of the Earth's crust, tearing away and thinning out a sliver of the ancient continent. By 76 million years ago, this extreme stretching triggers rift-related volcanism, creating those Padua Bank rhyolites we just talked about. Then fast forward to between 65 and 56 million years ago, and this already stretched, mechanically exhausted sliver gets slammed by the reunion hotspot. Because the crust is so weak at this point, the massive magma injection underplates the crust, creating that thick underground cushion. Finally, as the Indian plate keeps moving north, drifting further away from the heat source, the heavily modified ridge slowly cools down and begins to sink. Over millions of years of this gradual thermal subsidence, corals start growing on the sinking peaks, eventually creating the beautiful shallow atolls we see today. And that leads us to our final verdict. The tectonic data is clear. The Laccadive Ridge is absolutely not just some simple trail of oceanic volcanoes. It is a true Frankensliver. It's a torn, heavily stretched out fragment of the ancient Darwar Craton, the literal geological heart of the Indian continent. It was violently ripped away during the breakup of supercontinents, and then it was permanently disguised by a massive injection of hotspot magma that completely and fundamentally altered its deep architecture.
It really makes you look at a map of the ocean differently, doesn't it? I mean, if a 2,500-kilometer stretch of continental crust can literally hide in plain sight beneath tropical corals, completely masked by layers of ancient volcanic rock, we really have to ask ourselves, what other lost continents or shattered microslivers might be hiding right under our noses in the deep ocean, just waiting for the right seismic data and deep-sea drilling to finally uncover them? The tectonic architecture of our oceans is so much more complex than we ever imagined. Thank you so much for joining me on this explainer, and keep questioning what lies beneath the surface.